Hello class, in this video we will talk about segments from center to a chord of a circle. So what about this? That's what we need to find out. So first and foremost, we need to know that congruent circles exist if their radii are congruent. So as you see here, since the radii of circles A, the yellow circle, with radius 5 in measure, and we have another circle B here, green circle with again radius of measure of 5, so that means their radii are congruent. So it follows that circle A is also congruent to circle B. So this is how we claim that two circles are congruent, by their radii measurement being also congruent. You must also talk about the definition of a distance from a point to a segment. So if we need to identify the distance from any point to a segment, what is that? So look, point D here and segment EF. We can draw as many segments as we like, right? What segment do you want to draw? So I like to draw these three segments, green, red, and blue. But which one is considered as the distance from point D to segment EF? So as defined, it is the one perpendicular to the segment. So which one here is perpendicular? The green, the red, or the blue? So we have here an indicator here. So right here, this is the indicator that the red segment measuring 20 is actually the distance from point D to segment EF, the perpendicular one. In fact, the distance perpendicular from point to segment is the shortest distance. So again, in the example, the distance of point D to segment EF is 20, which is the measure of segment DH. Since segment DH here is perpendicular or forms 90 degrees as seen here, the indicator, perpendicular to segment EF. Now, let's talk about one of the theorems. So it is said here that the perpendicular segment from the center, so you can see here circle C, the perpendicular segment from the center to a chord. So if we create that perpendicular segment from a center to a chord, say chord OE, so what is happening here? It bisects the chord. So it bisects the chord, class. That means FO and FE here, the two parts of chord OE, they are equal in measure. So that's the theorem that we are talking right now. Now there's another theorem stating that the segment from the center of a circle, so from the center of circle to the midpoint, okay, say F here is the midpoint, indicator here, indicator that OF is equal to FE. That means F is a midpoint of chord OE. So what? So according to this theorem, that that segment from the center of a circle to the midpoint of a chord, which is OE, and make sure that the chord is not a diameter, of course, then it is said to be perpendicular. So this segment here from the center to the midpoint of the chord happens to be perpendicular, and it's somewhat like just the converse of the first theorem that we just talked about in this video. And that's just it. Now for the third theorem. So what is this? In the plane of a circle, the perpendicular bisector of a chord passes through the center. So the chord here, OE, and let's consider line FG. Let's consider line FG as the perpendicular bisector. That means it is perpendicular to the chord, and at the same time it bisects the chord. So FO equal to FE as indicated here, the markings. So it is said that it passes through the center. So the red here, the red line being our perpendicular bisector of this chord, the green chord here, OE. If you extend it towards uh, the center, it will really pass through the center for sure. So any chord, and you make the perpendicular bisector of that chord, that perpendicular bisector, 100% it passes through the center. That's just the third theorem is talking about. Now let's proceed with the fourth. So according to the fourth theorem, if a line and a circle are coplanar and the line intersects the interior of the circle, then it intersects the circle into two and only 2 points. So you have your line A red, line C green, and line B blue. So as you see, these lines passes through the interior, right? Right here, this is the part where it passes to the interior, the green and the blue. We see here that this line, red line, passes through 2 points only. Similarly, the line, blue line rather, also passes through 2 points, and the green line also passes through 2 points. And that is it. That is the theorem is all about. And last but not the least, in, in accordance with the theorem, the fifth one, in the same circle or in congruent circles, chords equidistant from the center are congruent. So in our case, let's just consider the same circle. So the chords equidistant from the center. So we have chord WX here and chord YZ. So equidistant, that means the same distance. So remember the earlier definition of distance from a point to a segment. So when you say distance, it should be the one perpendicular. So we can clearly see here that this segment here being perpendicular to this chord YZ class, that means this is the distance representing uh, from point C to this segment, or this is actually a chord. Similarly, you can see that this segment here being perpendicular to chord WX, that means that this segment represents the distance from the center to the chord. As you see, these two distances happens to be 12. So what can we conclude? So what is the theorem saying? That if the two uh, chords are equidistant, so chord WX is 12 units from the center, chord ZY is 12 units from the center. They are equidistant. So what is that? The chords are congruent. So the WX chord and chord YZ, they are congruent. So you see here the indicator showing their congruence. So as simple as that, that is what the fifth theorem is about. And as a summary again, these are the theorems that we just discussed in this video. And thank you for watching, class.